we're going to talk about I/O. And I/O is an order of magnitude worse than memory when it comes to being a bottleneck. Not only is it further away from the system, there's more buses and controllers and things to traverse before you get to the CPU, but depending on where the I/O is coming from, you have another problem. Different devices interact in the world in different ways. So, for example, your network card is an I/O device. Nowadays, with high-speed internet, you can stream gigabit speeds, right? Hypothetically, if your connection is fast enough, and that's pretty good. So you can actually feed gigabits of data into the computer through your network connection. It's pretty fast. Then you have your keyboard. Your keyboard is actuated by you, a human. And even if you're lightning fast typing, you're not going to get that thing up to anywhere near gigabit speeds. You're not going to get kilobit speeds. So that thing sits there most of its time completely idle until I come over and press a key and mess up my document that it's on. And that is extremely slow. So if you imagine that the CPU had to sit there and wait for the keyboard to do something, it wouldn't get anything done. It would just sit there waiting and waiting and waiting, say, oh, I pressed an A, did something for a lightning hair of a second, and then it was back to waiting. So this is a problem we need to figure out what we need to address. We don't want our CPU waiting for I/O or just not knowing what to do. We don't want to program it in. We don't want our program to say, at this moment, go check the keyboard. And at that moment, go check the keyboard. And at this moment, print something to the screen, refresh the screen. We wouldn't code any actual code. We just spend our days dealing with I/O. Plus, we have to know what devices you're using to code for them. So we need a better strategy. So we're going to talk about two things today. We're going to talk about polling and interrupts. Now, these are two methods we can use to have the CPU interact with I/O devices. The first is pretty simple. We're going to take our standard CPU cycle that we've talked about so far. We have fetch, we have decode, we have execute, and sometimes we're going to start talking about this one because we are going to use it in our 6502. It did come up in some of the examples when we were talking about the pipeline. Sometimes we have write back. Write back is simply the idea that as part of the instruction cycle, we might actually have to write some result back to memory. Your increment instruction, we're going to look at that one later today that we did in 6502. I want to say it's EE, I can't remember the opcode. The idea was it took a byte in memory, it incremented it, and it put it back in memory. That had a write back. All right, so this is an optional part of the instruction cycle, but it's often referenced. Now, what we're going to do here is we're going to say, well, every so often as we go through this thing, we're going to check for I/O. How often? Well, that's up to us. All right, we can say, I mean, this would be extreme. We could say every cycle. That's not going to happen. We could say every 100 cycles. We could say every 1,000 cycles. We could use time. We could say every second or every half second. We're going to check for something to do. This is called polling. So let's take our keyboard as an example. Let's say that I set a polling interval of 2 seconds. So what this means now is that every 2 seconds, the CPU will stop whatever it's doing. Let's say that we have a program in there that's calculating pi out as far as it can. And every 2 seconds, it's going to stop. It's going to say, oh, I got to check to see if the keyboard did anything. So to do that, we're going to talk more about this in a moment. To do that, I need what's known as a driver. I need a piece of software that knows how to interact with the keyboard. Don't worry about the mechanism just yet on how this works, but remember you have one CPU in this metaphor. Even if you did it multiple, it wouldn't matter. One of your CPUs has to do this. So to check the keyboard, it needs to execute the keyboard's driver. So that means that it has to stop what it's doing and do something else. This is called a context switch. So we're going to do that. We're going to, every 2 seconds, do a context switch. We're going to stop the program, put it somewhere. We'll talk about where in a moment. Put the keyboard driver in, run the keyboard driver, see if there's something to get from the keyboard, and then move on, right? Now, okay, that works, and then we're gonna go back to calculating pi. But if it happens every 2 seconds and I'm typing, that means I'm not gonna see characters until every 2 seconds passes. So I can type hello, and then it appears. And type dog, and then it appears. So it's not gonna feel very good as a user. It's not gonna feel very responsive. I could decrease the amount of time that it takes polling me every half second. It'll feel better, it's still gonna be choppy. But now I'm doing that context switch 4 times more often. And what if I didn't type anything? I've wasted my time, right? I wasted the CPU's time. So polling is not the ideal solution. Interrupts take that same idea and they say, I'm going to add a couple of things. First, I'm going to add a physical wire that goes from this keyboard to the CPU. So there's going to be a wire there. And that wire will be for no other purpose other than to signal what's called an interrupt. I'm also going to add to my instruction cycle an interrupt, part of the instruction cycle. So every time I get to the end of my instruction cycle, before I start a new instruction, I'm going to check to see if there's anything on the interrupt line. I'm going to say, is the interrupt line high? If it is, the keyboard wants my attention. I'm going to stop what I'm doing and deal with the keyboard. Now, in the old kind of school way of doing things, these were, and they still are known this way, but we don't physically set them up anymore, so we don't think of them. These interrupt lines were known as IR2 lines, and there used to be 16 of them that were available to you usually through your BIOS. So that little program that boots up your computer, your BIOS, and if you went into it when it started, you would set these things. So back in the 386 and 486 days, 286, if I went out and I bought a new Sound Blaster sound card, I had to physically plug it into the machine, turn the computer on, go into the BIOS, and assign that Sound Blaster to an open IR2 number. So that was one of those hard-coded etched lines in my motherboard that were available to me to be an interrupt. And all of them went to the CPU. So that's how that physical mechanism works. Now, today, it's changed a little bit. We have our CPU, and now we have what's known as an interrupt controller. And now, those lines that go to the individual devices, they're still there, but they all go to this controller. The controller manages how they get assigned, and that they do get assigned. And then there's one line from the controller to the CPU. So essentially this thing becomes a little cube. It manages the priority of the interrupts, and we'll talk more about that later. It says what one goes first. But on every CPU cycle, this thing can check to see if there needs to be something dealt with. So it will send one interrupt to the CPU for every cycle based upon whatever logic we give it. All right, so that's the idea behind an interrupt controller. Now, this is a much better situation because now I can ignore the keyboard until I actually press a button, at which time I can deal with the keyboard. But we need to know more to make this work. We need to understand that context switch. We need to know, how do I go from calculating pi to running the keyboard driver? Now, there's a couple of big concepts here that get reused a lot in computer science. This is the basis of it all. This is the physical mechanism that makes it all work. But if you guys take operating systems, you're going to learn that task switching also happens this way. An interrupt is generated by the operating system. It checks to see if it needs to run a new program. It goes on with its life. So not just hardware uses this interrupt concept. We're also going to talk about stacks a lot now. We're going to talk about the way that we store the context of the program so that we can come back to it. That same idea is used all over the place. When you make a function call from another function, you are using the stack. The original function's memory is going into the stack, and you are now working with a new function. And then if you get a stack trace and you actually do a stack dump, you're looking at that progression to the stack. It actually takes the stack and it dumps the frames out for you. We'll talk more about that, but we're going to see now how we actually do that context switch. So this part is a little bit easier to use some of the slides to show. So let me bring those up. And like I said last time, there is definitely a lot more to this in the video that I'm not touching on. So please do make sure to still watch it. This is not intended to be a concise summary of the whole thing. We haven't talked about I/O controllers. I'll try to maybe squeeze those in at the end. I haven't talked about the I/O data and address register, all those good things. So please do still watch that. All right. Video percent. So here's our instruction cycle. Here's another way to represent it, right? This one doesn't have decoded. I took it from a book that doesn't separate out decode, which I don't like, but doesn't matter. And it's still kind of more little man computer than anything else. But the idea is sound. We have an instruction cycle. We check for an interrupt at the end. If we don't have one, we keep going. Otherwise, we deal with the interrupt. Now, there's a little bit more here that isn't contextually necessary if we're doing this on a microcontroller. This is assuming that this is a full normal computer with an operating system, or even your phone or tablet. These have operating systems as well. But as you'll see if you do OS that's elective, what actually happens is that when you have an interrupt, you switch to what's known as kernel mode. So normally when your program is running, you're in user space, meaning that your program has control over the CPU. Switching to kernel mode makes the CPU protected, user programs can no longer affect it. The operating system gains control. The operating system manages pushing your software onto the stack, but that can be hardware driven on a microcontroller as well. And then it loads up from a place called the interrupt vector table, the address that it's going to go to run the driver. That's the part I want to look at now. So there's two terms we need to know here. Interrupt vector table and interrupt service routine. That driver I talked about, that's the interrupt service routine. It's just a longer way to say device driver, but it's a more correct way to say it. So this is the program that understands how to run that particular device. So whether it's your hard drive, your keyboard, your printer, whatever it is, it has driver. To know how to find that driver, we have the interrupt vector table. This is a simple lookup table. And it is located in memory in a specific place where it's nowhere to be found, either by the hardware or by an operating system. And it looks something like this. It has the interrupt number. So let's just say we start with 0 for IRQ 0, 1, 2, etc., 3, ... And for each one, a corresponding memory address. So let's say in 6502, we say that FF00 is the first one, and I'm making this up. Let's say FF10 is the second one, right? And that might continue down. So if we get an interrupt, and if it's interrupt 1, we know to find the beginning of our interrupt service routine at this memory address. So now that we have this component, we can actually attempt to do the context switch. So let's take a look at what that looks like. Well, I'm going to leave it here, but I think I'm also going to kind of draw this out. So you have your program. It's running, it's calculating pi. On your program, you have data that's in different registers, right? So you have, let's say your accumulator has the number 5 in it. Let's say your X register, let's say you were about to print an integer. So your X register had a 1 in it. And let's say what you were going to print was a 10. So your Y register had an A in it, right? And you also have a stack pointer. We haven't talked a whole lot about that in class, but we did say that there's a stack register. There's some other things too, but very importantly, we have the program counter. So let's say your program was coming along and it was currently at instruction 00AF, right? Just for fun. So what we're going to do now is we say at the end of this instruction, we check for an interrupt. There is one. So now we're going to push all this information onto the stack. The stack is just a place in memory that is allocated for such an event. It can be done by the processor itself. So if you look at the spec sheets, there is an area of memory that is allocated for the stack from the hardware. It's just there. When you start up the hardware, that area of memory is designated for the stack. It can be done by the operating system as well, because remember, not everything has an operating system. So this somehow needs to be managed. So what it's going to do is it's going to take this information, and you'll see if you look at 6502, the full instruction set, not ours, because I purposely avoided the stack because we have one semester to do all this. Plus, you need something to learn in operating systems. I take all this and I push it into the stack. This becomes what's known as a stack frame, which is basically a collection of everything that I'm using right now in my registers, and it gets pushed into the stack. And there's an instruction for that. It's in the instruction set. So if we imagine memory here, we're specifically looking at the portion of it allocated for the stack. My first stack frame, we'll call it 1, and I'll put in parentheses here pi, because it's our pi running program, ends up there. Now, we come to our interrupt vector table, we grab the address for the interrupt service routine we want to run, and we take this and we pop it in the program counter. And guess what happens? It just starts running that program, right? So that's the basic idea of how this works. Now, you can have multiple interrupts happen, and there's a priority to them, so they can actually interrupt each other. So an example of that, let's imagine that I'm not going to do it because that would mess up the presentation, but if I pulled the power on this thing right now, believe it or not, that would generate an interrupt. There would be some milliseconds of power that that thing would still have provided to it by its internal capacitors and everything of that nature that would allow it moments in time, very minute ones, in which to react. And especially back in the days when there was spinning hard drives, and to be honest, this one might even have one. Desktops sometimes do because they're not laptops and it's cheaper. But when there was spinning hard disks, it was of paramount importance that if for some reason you lost power like that, that it did what was called parking the head. So those arms that moved across the spinning platters had to get back to their resting spot and off the platters, because if there was any movement at all, the thing could crash and it would damage the disks and it would be a bad day. So that's one thing that people would want to do with those last milliseconds of time. It wouldn't care about pi, it wouldn't care about what your keyboard interrupt was, wouldn't care about any of that stuff. That would be the only thing that matters. So that's an example of a priority, but there's more than that. There's priorities even to task switching and things like that. Your operating system might have its own priority above applications, etc. So our original program in this example is our pi, happily executing until interrupt A occurs. So we spend it, put it on the stack. So we got that one there. Now interrupt service routine A is running. Let's say it's your keyboard. It's running. All of a sudden, interrupt B happens while interrupt A was in the processor. Remember, you still have the same CPU cycle. You're still checking for interrupts at the end. So this time, it says, oh, B is more important, so A gets suspended. So again, we take what's in our registers at that moment, becomes a new stack frame, and A goes on the stack. Now we're doing B. B runs. That one actually completes. Cool. Now we pop A back off the stack and start finishing it. I think this one actually has yet another one happening. C happens, so A goes back on the stack. Then we finish C, A comes back off the stack. And then when A is finally done, we can take our pi program off the stack and finish it. So that is how we deal with context switches, but it's a lot more than that. And I like taking this moment to talk about that because it is very likely you talked about stacks and data structures or elsewhere along the way of your science education. However, I don't know that you've ever maybe had it tied in to the actual way in which you're coding programs. So I want to take a moment to talk about the stack and try to drive home their differences now because it's a good chance to do that. So the way this works, you might be aware, is that and it doesn't matter if the stack comes down from the top or up from the bottom, that's irrelevant. But we have memory, and some portion of the memory is allocated for what's called the heap. And the rest is allocated for the stack, which grows towards the heap, whether it's up or down. when you reallocate memory, you can insert more memory in between, but that's not what we need to worry about here. I just want to talk about the base concepts of what these two things are and when we use them. Let's imagine you have a program running. I'm going to use like C, Java-esque function names, but it doesn't matter, you know, what programming language they're in. So you start with a main function, right? When you're running that function, everything in that function that you're currently working with is usually in the registers, right? Or it's in specific places of memory that are in the scope of that function. Let's say your main function calls function 1. So within here, we have a call to function 1. When we do that, we take everything that's in the registers and everything that's currently in scope of that main function, and we push it into the stack. Just like we talked about with the interrupt context switch. So you now have main down here in the stack. Now let's say in function 1, you call function 2. Same thing happens, function 1 goes onto the stack. Now, obviously they're going to pop back off in the reverse order of how they came out. It's a last in, first out situation. If function 1 or function 2 calls function 3, function 2 is going to go on the stack. But then if function 3 finishes, then we're back into function 2, and then maybe it calls function 4 down here, right? Then function 2 is going to go back in the stack. You know how this works. Now, I want to bring back passing values into functions, parameters, and value and reference. Now, if you had me in SD2, you might remember that I worked a lot on the difference between passing my value and having a reference. So if you remember, having a value of something is the actual thing, right? So if you change it, it only changes that thing that you have. It doesn't change the original setting. You passed it by value. You said, here's the value, and you have a value. If you change it, you change that value. But the thing I had is the original, and it's not changed. Reference means that you change the actual thing. So if I give you a reference to something, let's say you are in main, and you give a reference for a variable a, and you change that reference in function 1, you've changed it for main and function 1, right? This is different from passing a. We know that in most programming languages, if not all, primitives are usually passed by value, and complex objects are passed by reference. So why is that? What is the functional difference that's happening? Value uses the stack. These things move around and become individual members of the stack. So if A is in main, and I pass A into function 1, right? And I change A in function 1, I did not change it in the stack frame. I changed it only in function 1's version of it, right? So I passed A, I said, here is a copy, a value that I want you to work with. When function 1 changes A, it's only in the scope of function 1 that A has changed. Why? Because it's in its stack. However, if I have B, and B is a user object, and in function 2, or whatever function we want, we change that, whether because we referenced it directly with a pointer, as they do in C, or because it is a complex object and therefore not stored in the stack. The reason why this is by reference and that changing it anywhere here changes it for everybody is because where it actually exists is here. What a reference is a reference to something in the heap. So in here is B, and B is the user, and it takes up some amount of space in the heap. And when you're talking about B in any of these functions, you are making a reference to the same place in the heap. But a value, like A, that is passed around by value, exists separately in these different stack frames, right? So changing in one does not necessarily affect the other. You would have to actually affect the other on purpose by changing it. All right, so that same concept of how we use the stack and the heap, it applies here, but it applies everywhere. So I know the heap doesn't necessarily directly apply to the interrupt piece, but I like taking a moment to kind of bring that in because we're here and we're talking about the stack and how it's used. So again, when you're looking at a stack trace in Java or TypeScript or any language, what you're seeing is, something went wrong here. I was running function through, something blew up, so your stack trace spits out every call that goes down this line to show you exactly how you got up to that point, right? So you can trace it back. All right, any questions on that? Yeah?
What happens if function one, so you modify its value, right, and you return it? How would it do that?
So when you return it, what happens is, remember, when you return a function, the call to the function is replaced by the value you return. So that means that you would now have it in the frame of the function that you returned it to. So it would now become a value within that frame. All other rules still apply, it's just you've now, given it to that frame, kind of like when you pass it in to a parameter, you're now giving it back through the return. Any other questions? Cool. All right. So that is the basic idea of how an interrupt works. And it's also quite a good aside on how the stack works. I want to show you one more thing here. So this is a good example of kind of how this looks in practice. We don't use Arduinos, unfortunately, this semester, obviously due to COVID. But I like to use this example because it's a perfect example of how polling works. And interrupts. Anyone actually used an Arduino here in the past, or even seen one and like played around with it? Okay. So if you've ever touched one, you might know that all Arduino programs have two functions at least. They have setup and loop. Setup is very simple. When you turn it on, setup runs once. So that's where you initialize your variables. In this case, we're saying that all the I/O pins on the Arduino are going to be used, one for a switch and one for an LED. We're saying that the switch is input and the LED is output. That's all we're doing. The setup happens once. That's the important part. It's your initialization. Then you have this loop. This loop is equivalent of the Arduino's CPU cycle. You get to write it because it's a microcontroller. The rules aren't written yet. You get to say exactly what happens in that loop. But the loop is every cycle of the Arduino. So, and it's actually interesting because when people first start coding for Arduino, they want to take all of the natural ways that they program, and one of the natural ways that we've all been programming forever is to use looping, right? To use iteration, but you're in a loop. So if you were in a for loop in here, you have a loop in a loop, and you're stopping the natural process of what the Arduino wants to do, which is constantly keep cycling through everything, and you're forcing it to do this sub-cycle, and that usually breaks things because it's not checking all the other inputs and outputs and things that it would normally check. So just as an aside, what we want to do in that situation is not loop, but just have an if statement that checks the condition you were looking for, right? Because you're already in a loop. So this is our polling example. So every time the Arduino cycles, we read from a pin, the switch, to see if you press the switch. So every time you go past this loop, you see if you press the switch. This is actually a good example, by the way, of what I was just talking about. If you imagine I had a loop here right below this, you would never check the switch again until you left your loop, right? So that's why you don't want to loop. So now that we've checked the switch state, we've recorded here, and we call our function here, update LED. We pass in that switch state, one stack frame to another, and now our update LED takes this information in. And by the way, remember when we talked about system calls and we said how information is passed from one function to the other, that we load it up into the registers first and then we call system call? You guys did this with the X and the Y register yourself. That's what you do here too. I mean, you don't manage it yourself anymore, but that's what's happening. You're passing parameters, you're putting stuff in registers, and the next function gets it. So update LED now takes switch state and it looks and says, is it low, or otherwise do this. So it basically just turns the light on if you press the switch. Otherwise, it leaves the light off. That's it. Very, very simple. But it loops, and it does this every single time. If we wanted to compute pi or something, we have to get creative, right? Because we're wasting all our time dealing with this, right? We're paying attention only to I/O. Now, normally on an Arduino, That's not a big deal because, you know, Arduinos are little simple creatures that are meant to perform very specific tasks, like automate my blinds going up and down, right? So it's usually okay. But here's a better way. Arduinos actually support interrupts. All Arduinos do this. There's varying amounts of it. Arduino supports like 2, the Mega supports more. But this is how you can write the same exact code with an interrupt. So if you attach the switch to an interrupt line, notice here that my loop is completely empty. I could calculate pi here, right? I can do whatever I want here, completely empty. I set up my pins the same, but now look at this attach interrupt. I have attach interrupt 0, the name of my function down here, and don't worry about the rising part. I'll tell you about that in a moment. But what do you guys think this is? From what we just talked about with interrupts and setting them up, and setting the drivers up so we can find them, what do you think I'm doing on that line of code? So this guy here, interrupt service routine, what do you think this is? What do you think it represents from what we talked about with IO? I mean, it's kind of in the name, interrupt service routine, right? It's the driver. So this is our driver, which means that this is how we assign it in the interrupt vector table, right? Here is the interrupt number, 0, and there is the place in memory, the reference to where we're going to find the driver, right? So this is for Arduino that doesn't know what IO you're going to hook up to it. This is how you create that interrupt vector table. It has a place in memory where it puts it, and it knows where to find it. But we're saying here that when you get IRQ0, fire off this driver. Now, this last one that I told you not to worry about too much, this is Arduino specific. But what it says is you can either do rising or falling, which means that the signal just happened or the signal is going away. So if you imagine the button, rising is when you press it down, falling is when you let go, right? So just like a mouse drag or something on the DOM in the UI, it matters when you react to the event. This is just like event-driven programming. It's the same idea. So that's what this is. It's very simple. It basically sets the interrupt. Now, anytime you press the button, this fires off. Otherwise, you're doing this. And behind the scenes, the Arduino can manage it just like we said, using the stack and doing all of that. And now all of a sudden, we have an event-driven program that allows us to do a normal program all by itself. All right. So there's also a little video where I kind of grabbed that from, which was done very well, that describes that. So you can watch that for more information as well. All right. So the last thing I kind of want to talk about before we jump into the program, and this I'm just going to hit on quick, is we talked about polling and IO, but we didn't really talk about the mechanism to talk to the different devices. So as we said before, there is like 8 million devices in the world, and how do we take a situation where we have a CPU memory and connect it to anything? A monitor, a keyboard, a printer, all of it. Well, the answer is that we need something in the middle called the controller. So we can't possibly expect the CPU to know directly how the IO device works or know anything about the IO device. So all of these devices come with a controller that understands them. Easiest way to think about this is that spinning hard disk that I described earlier. That thing to work needs to spin at a certain speed. Only the disk actually knows what speed it's going to spin at. It could be 7,200 RPMs, could be 15,000 RPMs for a server disk, could be 5,200 RPMs for an old laptop. Varies. Somebody has to control the motor, somebody has to control the voltage to the motor, make sure it's spinning at exactly the right speed. Then it has the read-write heads. That, as I mentioned before, we need to park if something goes wrong, but we also need to move those over the disk so that as it spins, they can access all kinds of places on that disk. And then we need to activate them at the precise right moment when the data we want spins under them. We're talking minute fractions of a second, extreme detail-oriented stuff. Every disk is going to be different. You can't expect the CPU to understand or know how to do that. It would only ever be designed to work with one piece of disk hardware, and that would be it. So to abstract that out, we build a controller. The controller can manage all of this, and then the CPU just needs to know how to talk to the controller. How can the CPU talk to the controller? Well, turns out we have an answer for that. It's pretty much exactly how it talks to memory. We can use a I/O address register and an I/O data register, just like we do with memory, to talk to any I/O device. In fact, you might remember way back when we did Little Man Computer, we had 901 and 902. And in Little Man Computer, we said those are two different instructions, but I said, well, really, it's kind of one instruction and two addresses, right? Now, Little Man Computer didn't understand that there would be disks and keyboards and monitors. It just had an in and out box. So your addresses were the in and out box. But how it works in a real computer is that the address is the physical I/O device. So just like you have places in memory, you have devices connected to the computer, they all get an address. So I can take that address, plop it from the CPU into the I/O device to find it. I can put any data I want to transfer to it in its data register, or take data I want out from its data register, right? Just like you do for memory. It's the same exact concept. So there's some address space that's left open for I/O. Now, how they do this is different for every computer architecture. Interestingly enough, on the 6502, your 16-bit memory addressing is also your I/O addressing. There's no difference there at all. They're just addresses. So 6502 hardware would actually have some portion of the memory address space not used for memory, and that could then be used for other things. It was sometimes used for read-only memory. It was sometimes used for I/O devices, things like that. So you would literally put an address in for a memory address to access I/O. It works the same. You have an address register and a data register. You just need an address that is unique to that place. So that's not to say that most hardware works that way anymore. Most of it has separate I/O space addressing, but the idea is the same. All right, so I'm not going to go through this. Please do in the slides. It kind of goes through that in a little bit more detail, goes to the nuances of it. I just wanted to touch on the high level, and then we're right back to where we started. All right, let's talk about project. So, first thing to know is that there's a lot to do. So, I've probably mentioned this before. I'm very proud of it. I would venture a good, honest guess that I have no idea what you guys have done with your own side projects on your own time, but I would venture a good, honest guess that for your coursework, at least, this is going to be your most intense programming experience to date. So you have a lot ahead of you. What's behind you is nothing compared to building this pipeline. So these major goals here, there's obviously a few more of them than there were in the labs, aren't, however, as different as they might seem. Number 1 and number 3, for example, you're really going to be building these together. Number 2, we now know what to do with. That was the interrupt check. Number 4 is the only one that you're not currently prepared to do, although to be honest, I think you can figure it out. You had to, but this is the one that's going to wait for our last topic. So don't worry about number 4 until the end, but the rest of them, we can do. So that pipeline, let's talk about that. We have to implement pipeline. What do I mean by that? Well, we're going to start with that fetch, decode, execute this. So what I mean by that is that we're going to come back to this, and we have to build it. And understand how, we're going to use some examples. So in your CPU, remember you have your pulse, right? Your CPU is a clock listener. Every pulse of the CPU, that pulse fires. You're going to need a mechanism to keep track of which of these steps, and as we're going to talk about in a moment, there can be more. Let me get this thing out of the way temporarily because I don't think we can come back to it. It's probably in people's view. Oh, cool, now I have to repeat. Let's use this. There can be multiple some of these. We're going to talk about that. There can be multiple decodes. There can be multiple executes. We're going to come back to that. But you need to keep a track of which one of these steps you should be on at any given CPU cycle. One CPU cycle does not mean you go through all of these. One CPU cycle means you go through one of these. And then you have to set yourself up so that on the next cycle, you go to the next one for that instruction. So let's kind of mock this up a little bit. We have our instruction register here that we know we're going to put the instruction in. We have a program counter, the accumulator and X and Y are super important for this, but I'll probably use them. And those are the major ones that I care about right now, and I'll add stuff as we go. So let's imagine that we also have our program. Let's imagine that we're going to start with a super basic program, A906, right? That's it. We got two things, an opcode and an operand. We're going to put the number 6 in the accumulator. That's all we're going to do. So on CPU cycle 1, you can always initialize your computer for its current step of the pipeline. This is your pipeline for its current step to be a fetch. You can always say, when I start off, I start with fetch. That is a given. So you're going to get this thing from memory, right? You're going to use those cool functions you've created now in your MMU, and you're going to pull this thing out of memory address 0000. And why is it that? Because we know that's what will be our program, right? So we're going to take this thing in the fetch, and we're going to put it in the instruction register. That's the end of the fetch, right? So now we're going to have some way in your CPU. This could be an enumeration or something, right? This could be like, these are the options in my pipeline. There's going to be more, like I said, there's multiple of these. But you're going to need a way to know which of the steps you're on and which one you should be on next. So there's going to be some local member here, like current step or something like that, that's now going to point to decode. Then you're done. You wait for the next CPU cycle, right? This is not something that you automate in chain code. It's a process that happens on every pulse. So now the next time there's a pulse, you look first to see what step you're on. You see that you're in decode, which means that you come over to the instruction to know what to do next, because every instruction's decode can be different, depends on how many operands it has. And for A9, we know that we have one operand. It's a constant, and it's going to very simply go in the accumulator. This is a very easy one. So for our decode, we're simply going to do another graph from memory. We're going to get this 6, and then the 6 is going to end up in the accumulator. This one is interesting because it's almost like decode and execute are kind of together because it's so simple. In getting the thing, the place that we're putting it is the result. So it's actually done. We're good. So now we have to set ourselves up for the next cycle. We finished actually doing the thing we need to do, so this kind of got pushed together. I would recommend what I do in this situation is I actually, from my decode, in my decode I have all of my MMU related functions that actually call the thing from memory and get it. But then the assignment to the accumulator, I from decode call execute directly. I call like this.execute, pass it the thing, and have it put in the accumulator, just to kind of separate the concerns. But it's fine as long as you get it done in the right amount of clock cycles. I'm not going to be too nuanced about it, where the actual write to the accumulator happened. If it happened in decode or write back, it doesn't matter. But you're going to need to know for each of these pipeline cycles, for this instruction, this happens. So you're going to need some kind of if statements, case statements, whatever it is, to manage all that. The next thing we're going to do is interrupt, because remember, we always do interrupt. Now remember, let's think about this way. We've done clock cycle 1 was our fetch. Clock cycle 2 was, I'm going to put decode plus execute, because it just so happened it all happened at once. And now we're on clock cycle 3. But one thing we didn't talk about, which is going to be interrupt. one thing we didn't talk about is that program counter. The program counter does not move in lockstep with the number of CPU cycles. The program counter moves in lockstep with when you access the program in memory, whether it's an opcode or an operand. So, when we did our initial fetch, one thing we neglected to say is that as soon as we got the thing from there and put it into the instruction register, we also incremented our program counter, right? Then, on clock cycle 2, when we went to get the operand, as we got the operand and put it into the accumulator, we incremented our program counter because we had to go to get the next thing. Now on cycle 3, we're not accessing memory for the program. So we're not going to increment the program counter, right? Interrupt doesn't need to increment the program counter because it's not going to memory to get a new instruction. We don't want to skip the next thing, right? We don't want to end up on 4. We want to make sure we're still here. So now we do the last piece of this instruction, which is the interrupt. And you're going to, this was bullet 2, I think. You're going to implement this, but I would leave the actual, for now, just have a place in your cycle for interrupt, and we can come back to that. We're going to kind of work through that over the next week or 2 after we get this started. So now you're going to say, okay, that first instruction is done. I'm going to reset myself to fetch. And let's say our next instruction is 8D4000, our favorite. So now we're going to take whatever's in the accumulator and we're going to store it into memory address 64, right? And that's it. So we do the same process. We do our fetch, we get the 8D, we put the 8D in our instruction register. We increment our program counter, right? Now we're done with that cycle. We have to set up for the next one. So we say the next one will be decode, and that clock cycle ends. Now on the next clock cycle, when the pulse happens, we wake up, we look to see what step we're on decode. We look at the instruction register to know what to do with the decode, and we see it's an 8D. This one's different. Now I have 2 operands. So on this clock cycle, we can only deal with one at a time. This is what we were talking about with the MMU when we set up that high and low water byte. I think that's the one I have the most questions on as far as like, why are we doing this? This is why. Because now I can only get this one on this clock cycle. So this decode 1, is going to be to grab this guy and put it into the low water byte in the MMU. I'm just going to put MMU.low water byte, right? So we're going to put that guy in there, the setup. Now we're going to increment the program counter because we did go to memory to get program code. It's an operand, but it's still part of the program. We're going to set this up now for decode 2 because we're not done decoding yet. Now we need another decode. And we're going to go on again. Next clock cycle. I'm on decode 2. I look at my instruction register, 8D. So I know I have a second operand to get. And I know it's going to be the high order byte because I'm on decode 2. So I'm going to grab this guy, and I'm going to do MMU.high order byte, and I'm going to pass it in there. I'm going to update the program counter because I did, in fact, go to memory to get an operand. I'm going to reset this to be an execute. And I'm going to wait for the next clock cycle. Now, what's the question? Not yet. I mean, there's probably some variances in how you can do this. This is just to kind of run through the logic of it and what happens at each step. Now, for the execute, everything should be set up. The execute for this is to actually put the thing in the accumulator into memory. So if your question was about like the timing and the memory data register and that kind of thing, that I'm actually going to talk about now. So remember that bonus that was in lab 3 about getting memory to follow the clock cycle timing? Well, this is why and when that matters. Because if you don't do the bonus, you can live in an imaginary world where I just take the accumulator value, stick it in the MMU's MDR, activate memory because these two things are available to me now, and the MDR, right? And it's going to write that thing into the correct place, and I'm done. But if you do the bonus, you have to deal with the cycle timing in memory. So you have to write to the MDR, you have to wait for that to settle. And then you have to write to memory, right? And if it was read, there was an additional settle because you would put the MAR in, get the thing to the MDR, wait for that to settle, and then pull it back out. That would be 3 clock cycles, right? So if you do the bonus, you got to think about the clock cycles as they relate to memory as well. If you don't, you can kind of skip that and everything just happens in the execute, right? I do the execute, I put the accumulator, MMU, set the MDR, and I'm going to put the 6 in there from the accumulator, and then you do your MMU.write, right? So I'm going to write the 6 to this memory address, and at that point, I'm done with execute. I'm going to set it to interrupt. I'm going to, do I update the program counter? What do you think? No, right? Because I didn't actually go to any program code. The execute happened without getting anything new. No operands were harmed in the creation of this action, right? So that's what I was saying before. The program counter and the CPU cycles do not move in lockstep. There's separation there. You only up the program counter when you come to get something out of the program, whether it's an opcode or operand. If you're doing a step that is acting on what you've gotten out of memory, you don't up the program counter. All right, and now the cycle repeats. Let me show this example here. This is the longest one. So the shortest CPU instructions will take 2 cycles. Whoops, go back. The longest in our implementation, we don't have the entire instruction set, but I think it's actually the longest in all of the anyway. I'm not 100% sure of that. And this is again without memory in the mix, is 7. So remember that, is it EE? Yes, the increment or EE that we were talking about with the write back. That is our longest one. So let's take a look at just kind of high level what this thing is doing. So in order for EE to work, we need the fetch to get EE. We put in the instruction, 1 cycle. We need the memory address as the 2 operands that follow it. That's 2 more cycles. That's 2 decodes to get the memory address. Let's say it's the same 4000 that we've been working with. So now we're up to 3 cycles. Then we need to get the information from memory, put it into the accumulator, because to increment it, there's no adder in memory, right? We don't have an adder circuit in the middle of our DRAM. So we're going to get the information from RAM, put it into the accumulator. It has to settle. Then on a second execution phase, we can do the increment to actually up it 1 value to do the add. And unlike Little Man Computer, you don't need to worry about where the 1 comes from in the increment, because it is a actual instruction that the logic is hard coded into hardware. So it knows whenever you use increment to increment by 1, right? So that's not, you don't need to like put a 1 in memory somewhere. You did slow that. So now that has to settle so that we can then save it back in that write back that we talked about, back to the same memory location it came from. And then we need to do the interrupt check. So there are, count them, 7 CPU cycles that happen for this guy to take place. So that's the longest one. And there's some other complications too. All the fun you guys had with branching when you were writing the programs, you're gonna have more fun with branching when you're creating the branching itself to respond correctly to those 2's complement negative numbers, all that good stuff. I know. Took your soul out of it. It's battle. All right. So that's what lies ahead. Now, we haven't really talked a lot about the interrupt check. That we're gonna talk about in a future class. But that interrupt part of your CPU cycle, the end goal with that is that you're going to be looking for keyboard interrupts. So as you type, your program's going to be running, whatever it's doing, and then as you type on the keyboard, it will respond to interrupts and actually manage that through the CPU. And then that ASCII part, the last one that we haven't gotten to, that's just going to be the translation. So it's going to look up the letters ASCII code based on the keyboard code that you press. All right, any questions? That's a lot for 9 o'clock in the morning. All right, here's what I want you to do. Here's your action for the week. I want you to give this a good, honest try. I want you to start building your pipeline. I want you to attempt some of the smaller instructions like A9, no op. Some of the basic ones, maybe the transfer from X to accumulator or something like that. If you're feeling bold, you can go for one of the medium ones like memory operation that actually ties in with memory use. I need you to actually do this before class next week, so that, because if you come to class next week and you haven't actually tried it, it's not going to feel any different than it does now. So go, try it, do it, and then when we're here, we get to actually work through the questions that you have on why it's not making sense and what's not working. So that's the big goal for next week, is to actually start building the pipeline so that we have something to move forward from next week.